First speaker for this afternoon session is going to be Steve Figlewski from NYU, who's going to be talking about beyond Black and Scholes. What can the Q distribution tell us about the risk neutralization process? So please join me in welcoming Steve.
You guys can all hear me, I hope. Yes, sounds like. Wait a minute, where is the... There we go. Let me first start by thanking the organizers very much for putting on this fantastic conference, and especially for inviting me to speak at it. Now, many years ago, I was a fresh, young PhD student sitting in Bob Merton's Advanced Capital Markets course. And Bob gave me a piece of advice that stuck with me. I thought it was excellent advice. He said, Steve, don't ever commit to give a paper at a conference that you haven't already written. Now, throughout my career, I followed that advice to my advantage until now. And last spring, Andy Lowe invited me to give a talk at this conference, and there was absolutely no way that I could refuse. I could turn down this opportunity to talk at the conference, even though I didn't have a paper written. All right. Well, what I did have, though, was an idea, a line of research that I'd been pursuing on and off for many years. And so I had a good idea. I got a data set that was exactly what is needed for this kind of research. I had the time and the energy. Well, it turns out I didn't maybe have quite enough time, but anyway, I had the energy to write the paper that I wanted to write for a long time. I wanted to wrestle to the mat, if I possibly could, the wildly elusive Q distribution. Now, I think probably a lot of people here don't know what I mean by the Q distribution, although it has been referred to actually earlier in this conference. But everybody knows that you can take an option and the Black-Scholes model and the market price for that option and solve backwards through the model to get the implied volatility. If you have a bunch of options with the same maturity and different strike prices, you can get a bunch of implied volatilities. They all ought to be the same according to the model, but they never are. We get the volatility smile or the skew that showed up after the crash of '87. So there's something in the model, there's something that's missing from the model that's in market option prices but is not in the model. All right? What we learned back in 1978 was that not only can you get an implied volatility, not only can you get a volatility skew, but you can actually, from a set of options that have the same maturity and different strikes, you can pull out the market's entire probability distribution over the final stock price at expiration of those options. That's the Q distribution. Now, the Q distribution includes what the market really thinks the probabilities are going to be. That's the P distribution, the market's best estimate of what the actual stock price is going to be at option expiration. That's the P distribution, but we can't see that. What we can do, though, is we can extract from option market prices, we can get the Q distribution. The Q distribution includes the P distribution, the best estimate of what the stock price is going to be at expiration, but it's modified by the market's risk preferences and everything else that goes into the market prices for options. Risk on, risk off, expectations that the Fed is going to do something weird next week. All this kind of stuff goes into market prices for options, and we can pull it out with the Q distribution. And it's not in the model. The model is the P distribution. So if we want to go beyond Black and Scholes, what we want to look at is the difference between the Q distribution, that's the distribution that somehow is getting, the market is put into option prices, and the P distribution, which is, at least the best we can figure out, what is the best forecast of the probability distribution of where the S&P is going to be at option expiration day. So that's the object of my paper. Now, I'm embarrassed to tell you that I'm presenting a paper here that isn't finished yet, and this is like the roughest of rough drafts, and I will publicly thank my discussant, Emanuel Derman, for his extreme patience while I was going through this process. But I feel okay about this because what I really want to show you is a new kind of a technology, or at least a way of managing the data that we have available to us from the options market that I've had such trouble with over the years. And so I'm going to try and give you what I've come to as a way of extracting information from the entire set of option prices by looking at the difference between this Q distribution and the P distribution. All right, so here's a plan of what we're going to do. First, I want to show you how one extracts this Q distribution from option prices, and then I want to tell you about how I want to set up what I will regard as a benchmark, the P distribution, that is what is embedded in principle within the Black-Scholes model. Now, once we got the Q distribution, we can look at how they differ, and you'll see, spoiler alert, a couple of things. The Q distribution has a fat tail on the left side. This is not a big surprise. It's highly negatively skewed. The log normal is positively skewed. This is a big difference. And the thing that surprised me the most of these results is that when we have this idea that the market is fat-tailed, it's not fat on the right side. It's very thin on the right side, not as fat as the log normal. And you'll see this in the picture in a second. All right. Now, we've got all what from Black-Scholes is based on the no arbitrage principle. Black-Scholes doesn't actually fit the data, as we know, right? So now people have been trying to introduce new variables, more elaborate data generating process, for example, that gives us less of a skew, less of a smile. My feeling is that these kinds of efforts to add more and more returns-based variables to explain option prices have kind of come to a point of diminishing return, and we're not going to get a whole lot more out of this. And what we really ought to be looking at is the stuff that isn't in the model, the stuff that no arbitrage rules out, but real world arbitrage is hard and doesn't rule out. Things like market sentiment, emotion, expectations of what the Fed's going to do next week, and all sorts of things like that, that are not in the basic returns-based no arbitrage models. One of the things you get from the Q distribution is that you can also look at how market sentiment and these kind of other things that are ruled out of the model may actually get into option prices. So I'll show you a couple of examples. One with, I'm going to put in a couple of sentiment variables. One is the yield spread on BAA corporates versus the 10-year treasuries, and the other is a Michigan Consumer Sentiment Index. And we're going to see both of those are highly significant in explaining the difference between the Q and the P distribution. And then finally, because the Q distribution is available every single day, and in fact, even intraday, as long as there's options trading, you can calculate down to the 1 minute level, then is perfect for things like event studies. You want to see a piece of information here. Next Wednesday afternoon, the Fed is going to have an announcement of its new interest rate. This is going to make a big impact on the market, and we can look in the options market, look at the Q distribution, and see exactly where that's going to have its biggest impact. All right. This is my favorite slide. You may have noticed that I jumped past it immediately because I always spend much too much time on this, but I like it so much because it's the theory behind how you can extract the Q distribution from option prices, and it only takes 1 page. This was from Breeden and Litzenberg. Oh, all right, I'll show it to you. There it is. We start off with a couple of equations, but very quickly we come to something very simple. Here's the Q distribution is just the partial derivative of the call option price with respect to the strike price. The strike goes up a little bit, the option loses a little value, and from that we can deduce what the risk-neutral probability distribution, the Q distribution, is. So the other thing I didn't mention is how I could get excited about doing this is that anybody who's tried to do this stuff, the data is really hard to deal with, and you're going to see this in a second. But this market, the market for the E-mini, it's the E-mini futures on the S&P 500 and options on those. This is the market in the real world that has, as far as I can tell, about the best approximation to the frictionless markets that we build theories out of. Transactions costs are tiny and it's very actively traded. So I've got 23 years of data on the quarterly maturities. These are the most active ones. Third Friday of the March, June, September, and December. They expire. The futures contracts at expiration are set equal to the S&P 500 index. So these are essentially derivative contracts, futures and options, on the S&P 500. And the Q distribution is a distribution over where the S&P is going to be at option expiration day. We use all the calls and puts. One of the things you need is that you need a lot of options. And I don't want to overdo my time here. You need a lot of options to do this. This market has on it, I'm going to show you for one day, over 350 traded strikes for the same maturity of March. We're going to look at the January 18th, 2023 Q as an example. Use all calls and puts. 10 days to 90 days of maturity with the average of about it's about a month and a half. And option prices, use all of them except I threw out anything that where the average between the bid-ask spread is less than 10 cents, which throws out a lot of really illiquid stuff. For other kind of variables inputs, we need interest rates, so I use 3-month treasuries. I got the S&P index and historical level of the VIX from Yahoo, and the other data. Moody's, some comes from the St. Louis Fed, and some comes from Wikipedia. I showed you very, very briefly that formula for the Q distribution. Well, if you want to implement it, we're taking, instead of the partial derivatives, we're taking actual discrete changes between, this is for puts, a put with one strike price and a minus a put at a lower strike price. There's a little adjustment that I've developed that takes account of the fact that we're talking about discrete changes and not DXs in changes in the strikes. But you can see that implementing this, you got to start subtracting option market prices divided by the difference in strike prices. If you do that, this is what you get. This is for one day, January 18th of this year. The black is the P distribution. Now, I told you, perhaps I told you that I've been struggling to try and get this talk down into the available time. I went home last night and threw out half of my slides. One of the slides I threw out, I shouldn't perhaps have thrown out, which is, how in the world do I make the P distribution? Well, I'm going to start with the Black-Scholes model. I'm going to say, suppose I really wanted to use the Black-Scholes model to trade. Well, I need a volatility input. How am I going to do that? I'm going to look back over past history. I'm going to look at what historical volatility, I have to forecast some number of days in the future. Let's say I have to forecast 30 days ahead. I'm going to look back and figure out, making a 30-day forecast by combining historical volatility, realized volatility, and the VIX. So I put those two things together, run a regression to get the combination of VIX and 25-day historical volatility that would have given me the best forecast for the horizon I'm interested in. All right, so that's how, and then I stick that into the Black-Scholes equation, and that's the P distribution. There it is. It looks pretty nice. This one here, the red one is the Q distribution coming from call prices, put prices, and the blue one is from call prices. Now, I really want to know, I really want the density, right? So I'm going to compute the density from the distribution function. Here's what you get. No, I don't. Wait a minute. Here. So the blue is the average of the put call Q distributions. The black, nice shaped thing, that's the P density. And that red stuff is what happens when you try to get the Q distribution out of that data. This is where most people end up stopping. And in fact, it's even worse than it looks like, because I've cut out the negative ones by just showing you it at 0. So anybody that actually pursues this is going to have to try and smooth the data somehow. And there's a lot of different ways of doing it. One of probably the most standard way of doing it is to say, this is too complicated. I'm just going to I'm going to assume that it's some particularly known distribution. I'm going to fit that distribution to the data. Right? That might be student t, it might be normal inverse Gaussian, it might be something else like that. But still, we're going to impose a shape on the data. I think this is a mistake. And when you look at what the cube distribution does from minute to minute, from day to day, there isn't any kind of standard density that we're familiar with that is actually going to follow what that actually does. So I think a better way to do is you compute the Q distribution and the risk neutral density, this is the density of the Q, and compute that from the data and then smooth what you get. And I think smoothing the distribution function is better than trying to smooth the density. All right? But I did come up with a new way of smoothing this that I don't have time to talk about, so I won't. All right? But the basic issue is this, that if I think that a lot of my data errors are coming from the fact that I've got to get prices for the options that are discrete at 5-cent intervals or 25-cent intervals or something like that, puts a lot of errors into these things. You start subtracting one option price from a nearby one, that puts a lot of error into the difference, and you could see what it turns out to, right? If you take over wider intervals, the observation errors on each price stay the same, but the denominator gets bigger, and so you end up increasing the signal to noise ratio. And whether that made sense to you or not, this is what happens. This looks better than the last one. If you take this is taking differences over three steps instead of just one. And now if we take the derivative of that, also smoothing again, you end up with something you can almost use, which is that. All right, now the red is my smooth Q distribution. It actually looks reasonable, and there's three things to see in it that are worth looking at. One, the left tail is fat, right? Two, it's highly negatively skewed. And three, what surprised me is the right tail is way lower than what would be suggested by the P distribution. Now so when we think about, well, you say returns a fat tail, well, maybe the returns a fat tail, but the Q distribution isn't. It's only fat-tailed on one side, and it's not fat-tailed on the other side. All right? One thing that happened in here that I should point out, when we look at this one, we're centered on the futures price, which at this time was about 39.40. Right. But if I want to compare Qs from different days, I need to standardize them. And so I standardize by dividing by the futures price and convert these all into gross returns. Stock price at end divided by today's futures price. And so all these things are going to have 1 as the central point on the horizontal axis. Oh, now, so that was for one day. Averaging across all of my data, I end up with this, which looks almost reasonable, right? And here's the density. And obeys what I've just told you. Fat left tail, highly negatively skewed, thin right tail. Now, the next thing I'm going to show you is how this Q distribution changes in response to the things that we put into no arbitrage models, namely return squared, jumps, and maybe allowing negative returns to be different from positive returns. But the results are going to be all on this kind of a scale where the futures price is always going to be the central point. The P distribution says the underlying follows a martingale, right? So the P every day is going to be still the mean of what's expected for the future. But I want to show you what happens when a day goes by. The red, this is the day before the one we've been looking at. This is January 17th. Here's January 18th. 17, now add 18. Now up above, we see, yes, of course, everything moves to the left. The market went down 1.6% this day. Right? But the P distribution moves too. And what I want to look at is the difference between the P and the Q. And now we see that on the bottom, once we've standardized, it doesn't move quite the same way. And about the one place you see it moving is right here. Right? So in interpreting the next things I'm going to show you, keep in mind that we're looking at the standardizing, how the shape changes, not necessarily moving. Now, here's where I show you, look, here, I broke up the Q distribution, or the density, into 11 buckets defined by probabilities. And we're going to look at the probabilities at the breakpoints of the buckets and also within each of these buckets. And having said that, I'm not going to show it to you at all because you've already seen it in the picture. What I do want to show you, though, is what happens when we start adding explanatory variables to this. And rather than trying to take you through 11 different buckets, we'll just look at two non-parametric statistics, the median instead of the mean, because we can't get the tails of the distribution. We can only get the part of the distribution where there's traded option strikes. So we're missing the tails. We can't compute the mean. We can't compute the standard deviation, but we can compute the median, and we can compute the interquartile spread between the 25th percentile and the 75th percentile as an alternative measure to standard deviation. So, whoops. Just looking at the change in the Q median as a function of log return. Highly significant variable. You get a negative return times a negative coefficient. The Q median goes up. Wait. Positive return, Q median goes down. Now, this is one of these things where this is a kind of unusual result, and don't sort of think that it partly has to do with the weird shape that the Q itself has, that the tail may move and may move the mean. I'm not quite sure what's going on here. But when we look at our risk measure, the change in the spread, negative return times a negative coefficient says the spread gets wider. Positive return gets narrow and highly significant, and this carries through to a lesser degree when we compare it against the P distribution. Let's try and add, I added these other things one at a time, but I don't obviously have time to talk about. Let's see what happens when we add jumps. Turns out that as far as the Q distribution is concerned, a positive jump means more than a negative jump. Positive jump, highly significant increase in the Q median, and an increase in the Q median relative to the P median. The positive jump, risk goes down, and relative to the P, it also goes down. Right? Negative jumps turn out to be a little bit anomalous and maybe start to ask a question that do I really have the best measure of the P distribution for looking at this? And the reason I wondered about this is that in forming the P distribution, I put in a lot of the VIX. The VIX has all of the same option prices that the Q distribution has, but they've been squished together into a single number that's hard to interpret. If you look at the whole Q distribution, you get a much prettier thing. You have some better idea of what's going on. All right. But since my P distribution also has the VIX, it's got some of what I'm trying to measure with the Q. And I'm not sure that I've got everything right just yet. In fact, I'm sure I don't have everything right. And let me say at this point, I welcome everybody's ideas of what I really ought to be doing next. But I wanted to show you one more thing. Here's another or two more things. One complicated table. I'm not going to tell you anything about the numbers in it at this point, but just to show you what it is that I'm looking at, I wanted to add other measures of market sentiment, the yield spread on corporates and the Michigan survey, and look at the Q median, the change, Q median minus the P, the changes in those things. This is on the right side looking at, or excuse me, on the left side looking at sort of returns related stuff, and on the right side looking at risk related stuff with the interquartile spread. So what you're supposed to see here is that those coefficients with the log return and log squared are all pretty much the same, meaning that what I've added here with these sentiment variables doesn't change much of what was there before. And now, if we look at the change in the Q, when the yield spread on corporates is high, the Q median is low. When Michigan, this is an anomalous one. Let me skip that one for a second. When the yield spread is high, the interquartile spread for the Q is high. When the Michigan survey is high, people are confident, then the interquartile spread is narrower, right? So we see that, then these are highly significant. So we see that these sentiment variables are actually giving us some explanation of how options are being priced in the market that is not in the model. All right? That's the objective. I mean, I'm way out of time, I'm sure. So let me add just one more thing. This is really suitable for looking at how information releases enter in the markets. Event studies. Right? I did one 15 years ago or so, looking at, this was in in like 2009, right after the crash. And I had about 18 Fed announcements that, by looking at the Q distribution intraday in 10-minute intervals, you could really see. 2 o'clock in the afternoon, the Fed announces what the new interest rate target is. The market blows up immediately, does something big, within minutes, within seconds. And then for the rest of the afternoon, it's still bouncing around as it's trying to understand what its own reaction is till the end of the day. Well, what I did with this one is that I had all of the Fed meetings since 2001 and looked at the whole week, 5 days before to 5 days afterwards, and see what happens to the interquartile spread. You would expect that when a big piece of information is announced, this is resolution of uncertainty, and the thing should get narrower. Right? Well, I have a nice table, but a picture is worth 1,000 words, and I don't have time for 1,000 words anymore, so I'm going to just show you the picture. The blue curve there, this one, that's what happens on average, day by day, from 5 days before. Here's the announcement, intraday on day 0, and sure enough, the blue is for all of them, and then the red is when they announce an interest rate increase, yellow is a decrease, and the purple one in the middle is no change. And the thing that I find bizarre is that we see, as the week is going on, it looks like people are getting a good idea what's going to happen. It does happen. Between day 1 and day 0, there's a drop. Continues to drop, though. Things are still getting more and more confidence, and yet this is, whoops. That's Wednesday. This is Thursday. That's Friday. And then suddenly on Monday, everything blows up. What's going on? I don't know. Right? So there's plenty of room for additional research. All right, let me end here. But what I wanted to show you is that this is the technology people have been talking about for a long time, and it is a mess. And you saw the data, I took the best market you could get, and the data is a mess. And it still required a lot of massaging and tweaking and fiddling to get something that looked sensible. But when you do, you get something that is sensible and it's worth looking at. And that's what I wanted to show you. And everything that I've done here is really rough. It all requires a lot more refinement. But I think there's a lot of gold in those hills. And the Q distribution looks at, one of the things I really like about it is that, we put stuff into no arbitrage models and we spin the computer and so forth, and we come out with coefficients. But what the coefficient is telling us is sort of like, what ought somebody, how should they respond to a jump, for example? Here we can look at exactly how they respond to a jump, and we can see exactly what jump it was instead of just hypothesizing, well, it's a random draw from an exponential distribution or something like that. We actually can see what's happening. The Q distribution is available every day, intraday. Makes it great for looking at how a piece of information hits the market. It allows us to put in sentiment variables in an easy way. Right? And so you can tell I'm all pumped about this thing after spending the entire summer working on it, and I hope to inspire others to do so. There are lots of option markets in which Q distributions can be extracted, and more every day. There's a lot of markets, just even in this one S&P 500 space. There's many interesting applications for the technology, and I don't have to make a reputation anymore, so I figure that if I want people to work on this, I want to make the data available to anybody. All right? As soon as I'm satisfied that I've got the right technology for producing the data, I'm just going to make it available to anybody who wants to work on it. So, in the end, thanks so much for inviting me. Thanks for giving me the opportunity to do this.
I tried very hard to make this last exactly 10 minutes. Okay, I've spent my whole life as a practitioner and an academic working on extensions to Black Scholes, Merton, and applications, so I'm very, very happy to be part of this. Steve's tackled what's now a 50-year-old problem involving the meaning of deviations from the Black Scholes model, Black Scholes Merton model, excuse me. He's done it by enhancing a methodology that involves extracting and interpreting the risk-neutral distribution, as he just described, of the underlier of the option. The standard way before this, and actually continuing, of dealing with deviations from Black Scholes Merton has been to analyze the implied volatility smile. Steve's done it differently, and you've seen his preliminary results. They're really interesting. We're going to have to wait for the benefit of his methodology to emerge. He's been working on this for a long time. I used to show those 2008, 2009 figures of yours from changes through the crash in my class. Anyway, so meanwhile, I'm going to describe the problem, the traditional volatility smile approach, and Steve's method and its advantages and the relation between them. The problem with Black Scholes from this point of view is that it assumes log normality of the underlier, and we don't actually know the future log normal volatility. Black Scholes Merton needs that to construct a riskless hedge and obtain a riskless portfolio, and then to value it by no arbitrage. The snag is that A, returns aren't really log normal, and B, even if they were, we don't know the future volatility. As Steve said, he uses the VIX to figure out the future volatility and risk neutralizes it. So since there's no riskless hedge, risk premiums matter, and things tend to fall apart a teeny bit. You have to figure out how to deal with it. What have people traditionally done? As far as I understood from Fisher, Black and Scholes originally used historical volatility as a proxy for the future realized volatility. At least that's my impression. So that was one approach for tackling the knowledge of the future volatility. The next advance 3 years later, which many people have mentioned here, was by Latan and Rendelman, who invented implied volatility as a proxy for instantaneous future volatility, and suggested using that to calibrate the model and calculate hedge ratios. Actually, everybody thinks implied volatility has been around forever, but I want to say it actually was an invention. 3 years after Black Scholes, I once ran into Mark Rubenstein on Madison Avenue, the late Mark Rubenstein, before that, and I asked him about it, and he set me on the path to looking up Latan and Rendelman's paper. So this actually wasn't always the case. People invented implied volatility, and everybody talks about it as though it's normal, but it wasn't. But implied volatility is an unstable proxy for future realized volatility, though there is a correlation between the VIX and future realized volatility. Steve makes use of that correlation to get the P distribution, but he assumes log normality, and I just want to say that's not true. Then, along this historical path, 11 years later, in 1987, came the implied volatility smile. From then on, people knew that the Q distribution also isn't log normal. But nevertheless, people continue to use inconsistent Black-Scholes Merton implied log normal volatilities to describe this skew. I wrote a textbook once called The Volatility Smile, and I said, the Black-Scholes model sounds so rational and has such a strong grip on everyone's imagination that even people who don't believe in its assumptions nevertheless use it to quote prices at which they're willing to trade. It's a lot like yield to maturity for bonds. Rebinado put it nicely 25 years ago. He said, implied volatility is the wrong number to put in the wrong formula to get the right price. That's not meant to be an insult. It's a reflection of just how powerful the whole concept of the model is. It's a compliment. Before I continue, let me describe the traditional implied volatility view of stylized facts about the deviations from Black-Scholes that Steve is talking about. First of all, implied volatility traditionally tends to be greater than recent realized volatility. Secondly, there's a negative skew with strike, steeper for short expirations, flatter for long expirations. Thirdly, there's interestingly less variation in the skew when you plot it against delta rather than against strike, against Black-Scholes delta. And finally, a crisis leads to a drop in the market, a rise in all implied vols, a steepening of the skew, and especially a rise in the short-term put skew. So the whole surface slopes. What are the possible solutions to all of this? First, Steve mentioned adding stochastic factors to the Black-Scholes Merton model. The most ambitious aim is to get a richer model of stock price evolution that matches the real behavior of stocks and describes the volatility smile. That doesn't mean it just describes the marginal P distribution or the marginal Q distribution, but actually describes the whole stochastic evolution process. That would be the ideal solution. People have tried local volatility, stochastic volatility, jump diffusion, rough volatility, etc. None of them really work completely. It's very difficult to find the right process if there is a stable one, and it's probably different for different asset classes. And every random factor, as Steve said, you add to the whole system becomes a new source of risk that can't be perfectly hedged. So life is complicated. A second method, which I don't want to exceed my time. A second method is called a market model, where you actually try to describe in a no arbitrage way the actual implied volatilities, like market model for bond yields, and it's been done, but people don't really embrace it. The third method, enhanced by Steve, is to extract the marginal Q distribution from option prices via the famous Breeden-Lutzenberger relation. The Breeden-Lutzenberger relation, as Steve said, relates the density to the second derivative of the option price with respect to strike. It's a second derivative. Steve looks at the stylized facts and the sensitivities of option prices in terms of this Q distribution that he showed there, rather than implied volatilities, which is what people have traditionally done. It's a bit less ambitious than modeling the stochastic process, but may contain more information and may be more useful. So he introduces three new elements to model the Q distribution. One, he looks at the Q, he doesn't look at the Q distribution alone, he looks at Q minus P, the difference between implied and what he calls the real distribution. And that's supposed to capture the risk premium that elude the view of risk-free hedging. Secondly, as he said, he takes a non-parametric approach by extracting the distribution numerically via his 10 or 12 point differencing with great care and more exhaustively than people have done before. And finally, which I haven't seen before at all, he breaks up the Q minus P distribution into deciles and regresses the events in each decile against returns, return squared, jumps, FOMC announcements, etc. So I'm not going to comment too much on his early results. As he said, it's still early in the day. People do know that the Q distribution has a fatter left tail than the P distribution. That's sort of implicit in the volatility put skew, but there are more interesting details emerging from his analysis. Whoa, I'm going to finish early. So let me make a couple of observations. First of all, I'm repeating myself. The P distribution really isn't known. Even the P distribution that Steve gets is not the true P distribution, which is sort of what physicists, it's inherently subjective, as he writes in his paper. It's sort of what quantum physicists call a hidden variable. Nobody knows what the P, it's the first moment in a way. Nobody knows what the P distribution is. He assumes log normality and extracts the index volatility from a regression of future realized returns against the VIX and against past realized returns. But it isn't really log normal in real life. Who knows what the P process is? Nobody. This kind of bothers me as a scientist, if not as a practitioner. Secondly, the other observation, the Q distribution, the second derivative with respect to strike prices, actually it's got a very physical or visceral meaning. It's the price of a butterfly spread, of an infinitesimal butterfly spread. The second derivative is just the price of an option, of an Arrow-Debreu security, of a contingent claim. And so what he's doing is sort of complementary to look, and an Arrow-Debreu's butterfly security is made out of options and implied volatility, so it's a complementary way of looking at the same thing. If you look at the put skew, what you're really saying is that low strike butterfly spreads have more value than relatively more value than high strike butterfly spreads. So what Steve is doing is related but complementary, another way of looking at it. So my general conclusion about all of this, there'll never be a perfect model in which you can turn the crank and get the right answer. With every hedging model, you have to think about its imperfections in the way that Steve was talking about, and how you'll embed what you think about the market's behavior and the risk premium at this particular instant into the model's parameters at one instant. The great thing about Black-Scholes is that it gives you a small number of variables in which to embed your intuition about what's going to happen in the future. So I like to say the success of Black-Scholes Merton has been the story of a very elegant, platonic, asymptotically correct kind of simple model, but taken very seriously, and then used extravagantly with hubris as a crutch to human thinking. Does that mean my time is up? I've got 30 more seconds. There's a line from William Blake that I like: if a fool would persist in his folly, he would become wise. And I think that's not an insult either, that's a compliment. That's sort of what users of Black-Scholes have done by taking it very seriously and pushing it as far as it can go and then becoming smart in the process. And I think that's what Steve's doing with his Q minus P approach, taking something a little bit naive and pushing it as far as you can go. And I think that's a good way to proceed. It'll be very interesting to see what emerges as more people pick up on his data and as he continues. Thank you.